Okay, I guess we can start. So our next speaker is Dmitry Petrashko, and I'm not sure about you, but I'm really excited to see how Doty has evolved and what progress has been made in such a short time. And today we are going to see how Doty has evolved, and we are going to see some internals, as well as perhaps, if we have time in the future, in the end, also some practice. Okay, a round of applause for Dmitry.
Okay, hi everybody. If you want to follow me on your device, be it laptop or mobile phone, you can either go through the Google GL link or read this QR code. They both point to the very same presentation that I'm giving, and it's going to change slides when I'm going to change the slides. You can also go to the Doty repo, and there you can actually try and compile the examples that I'm showing you. So Doty is built by SBT, but you don't need to do it. There is a script inside the bin directory called dotc that you can use as a replacement for Scala C and just compile the files with it. You should be able to compile Doty in your machine the first time you run it. Okay, so what is Doty? Doty is a new compiler for Scala-like language. And by new, I mean that it's actually a rewrite. So it took some tools from Scala C compiler, but most of the stuff like type checker, like phases, is actually being rewritten from scratch. It's developed at LAMP laboratory of EPFL. That's the same laboratory that originally developed Scala, and it's developed by Martin Odersky and me. It's currently not ready for production use. We're still fixing bugs, and we're going to actually, after we're done with fixing initial bugs, start putting features in. So every new feature gives you potential bugs, so if you want to go with fancy features, maybe you should try Doty. If you really want to go with production use, then Scala C is the way to go for you for quite substantial time. So, and here we're exploring new technologies that may or may not actually find the way to future Scala releases. But because Doty is a lot easier to evolve, a lot easier to extend, that's a place where experimentation is being done. So who am I? That's my name on GitHub, Twitter, and everywhere. I'm doing my PhD at EPFL, so I'm starting my third year now, under supervision of Martin Odersky. Previously, I'd worked on Scala Blitz. Scala Blitz is more efficient operations for Scala collections, macro-based for Scala C, that you can use as a replacement to get your operations and collections to be faster. And since March 2014, I'm working on Doty. Okay, so to show that I actually know what Doty is, I can show you these stats. So around half of the current code is written by me in Doty. Almost every phase that you can imagine that exists in Doty has some of my code in it, and most of the tests and most of the bootstrapping of Doty is actually done by me. Okay, so my talk will be divided in two parts. In first part, I will cover what features an ecosystem changes are actually being tried out in Doty, and what are potential maybe extensions to the Scala language in general. Those will cover new extensions to type system, new extensions to syntax, new possible things like trait parameters. I will also say which parts of Scala language we currently do not intend to support. Then I will say how it should in generally change how the ecosystem looks like, including what are the other projects that are somehow linked to Doty and somehow friends to it. In the second part of my talk, I'll talk about Doty internals. This is the part that actually explains how everything that was in the first part actually works and why we're able to develop new things for Doty faster. Okay, so to have a quick start, the simplest feature that we have in Doty from the user point of view is end types. Using end types, you can actually say that the argument that you're taking is both A and B. In this example, for example, the argument is both serializable and comparable. You can actually try to write the same in Scala by saying with, but there is a slight difference. So with uses linearization to find out who takes precedence. So if you have two types, A and B, and both of them have members, then A will still take precedence. Unlike this, in end types, you say that the instance that you have is both A and both B, it means that it should have members that fulfill the requirements of both A and B. And then in this particular case, for example, the T inside should be both A.T and B.T, which is int and double at the same time. So though you can actually play around with this feature in Scala, you can't actually have the full force of it because it's not symmetric. There is another thing that we have as an extension of the type system, and this is OR types. So in this case, you're saying that the argument that you're taking is either of type A or of type B. And what you'll be allowed to do with it is, well, you can pattern match over the actual type and be able to see of all members after you're done pattern matching, or you can actually take the members that are present in both types. So for example, in the method foo, where you take something typed as A or B, both A and B have the member x. And if you'll take it, in either case you're going to get an integer. Unlike this, if you have an OR type between A and C, both of them have member called x, but the type of this member is different. So if you will take x, A or B.x, you will actually get a different OR type. So there is no currently Scala equivalent, as of my knowledge, that allows you to call methods on OR types. In Scala.js needs OR types for some cases, but it uses only in signatures. It doesn't allow you to actually call methods on them, for example. One of the really good use cases of OR tags that I really like is they are proper enumerations. Honestly, I'm not aware if there exists a single language which has implemented enumerations the way that I like them. For example, one of the features that I would want to have is if I have two enumerations. For example, I have days of the week which are weekends, and I have days of the week which are working days. I want to be able to merge those things to say that, well, they constitute a whole week. Using OR types, you can easily express it, because, well, you have OR types which themselves can be ORed between each other. And then you can use it as signatures, in return types, in types of arguments, in types of fields, and it just works. Okay. We also implemented several of Scala improvement proposals. One of those is the proposal which originally originates from type level compiler, and this is literal base singleton types. So for example, you are already allowed to use in Doty syntax that tells you that this field is of constant type 42. And with those constants, you'll actually be able to expose all the features that were previously able to use and allowed to be used only inside compiler. For example, if you have two constant types, you can actually sum them and get a different constant type that is going to be compile time checked. Constant types in Doty cover primitives, and additionally they cover strings. Also, because that's not some extension of the type system that was done at the last moment. We originally designed type system to be able to handle those. You can actually use all the features that normally work. For example, constant types can actually be inferred as type parameters, and the same goes with AND types and OR types. For example, in Scala, if has type, which is the common supertype of the values that you return an if branch or an else branch. In Doty, if has an OR type. Okay. The other proposal that we have implemented is repeated by name parameters. So in Scala, you have repeated parameters. When you say, I don't know how many parameters are going to be passed to the function, I want to be able to handle as many parameters as are ever passed. Additionally, you have by name parameters. When you pass by passing parameters, you don't trigger their evaluation. Unfortunately, in Scala, you can't combine those two entities. You cannot say, I'm passing some unknown number of type parameters that I don't yet want to be evaluated before the function is being called. In Doty, you can actually do it. The next thing is the one that I like the most, because currently when I write a class in Scala, I have a problem. Do I write a class or do I write a trait? And there's actually a huge chapter devoted to this problem in Martin's book of Scala and in many tutorials, and you have a lot of newcomers to language asking the same question. There's a basic limitation that we had here. Traits couldn't have constructors. Well, in Doty they can. So you can have a trait which takes an argument, and it could do something with the argument. Initialize fields, print it, or so. The problem is that this feature has some funny interactions. So let's say you have such code. So you have a trait which itself takes an argument, which is then subtyped by two traits which pass different arguments. And they take an object or a class and subtype two traits, which both of them actually initialize the super trait with some argument. The question is, what should be the final value of the field that's initialized, and how many times should it be initialized? We've iterated over it several times, and we ended up understanding that all people have different understanding how it works, and it's going to work in unexpected ways and introduce incompatible binary changes and all kind of crap. So in the end, we just disallowed traits to pass arguments to other traits. So the way you are allowed to write it in Doty is that only classes or object are able to pass arguments to traits. And this makes this feature binary compatible, source compatible, and it just perfectly works. Okay, the other thing that we have in Doty, I believe it's, so in Doty we're not only trying to extend the language in terms of introducing new features, we also want to make the features that you use every day work better. For example, there is a commonly used thing called lazy vals. Lazy vals in Scala C or in Scala, as a specification says, need to guarantee the fact that if several threads access them in the same time, they guarantee safe evaluation and that the lazy vals are initialized only once. Unfortunately, internal implementation has some problems. Let me show you one of these. So let's say we have two objects, A and B, and they have lazy vals which create dependency between each other, but don't create actual circular dependency. So from point of view of lazy evaluation strategy of the language, you should be able to evaluate this always. So the problem is that if it happens that two threads start to evaluate those lazy vals, the way it's actually implemented, and they grab a lock over the object which contains a lazy val. So it means if thread 1 started evaluating field A0, it's going to grab a lock around A. If at the same time thread 2 started evaluating field B.B, it's going to grab a lock around B. In the next step, when they actually try to access each other, they will create a deadlock. That's one of the funny bugs that you can occasionally find in production, that it happens, but never know why, because if you're going to rerun the same application, it's not going to happen. That's one of the Heisenberg bugs that's, I believe, are the worst evil. So, the other case where I believe that there is a place for improvement for Scala C is because you actually grab a lock on the whole object, you cannot initialize several fields at the same time. So let's say you have an object C which has two fields, both of which are lazy vals. One of these takes long time to compute. It makes I/O, does some network access, or just waits for no good reason. And there's another field which computes fast, and that's a common case what you do, for example, when you have when you want to solve the problem of initialization order, when you have simple computations that should run fast. The problem is that if the value which is slow to initialize started initializing earlier, you cannot initialize the second one, though they are entirely independent. So lazy vals, there was actually a proposal to change how lazy vals works in Scala C. It's called SIP20, and it's implemented in Doty. In Doty, lazy vals don't deadlock if you don't have actual circular dependencies between them. But the code which has circular dependencies between lazy vals is not going to work in any case. In Scala C, it just throws Stack Overflow. Also, the lazy vals in Doty allow concurrent initialization of fields. So if you're having several fields which are independent, but they just happen to be in the same object, they don't slow down each other. additional change that we made, which is actually an incompatible change, but I will talk later about how do we handle incompatible changes, is that lazy vals in Doty are not thread safe by default. And why we did it is because lazy vals, as we believe, are commonly used to fix initialization order problem. So if you have a lot of traits that mix in each other, it's very tricky to understand which fields get initialized first. And if you refer to an initialized field and start using it, you're actually going to have problems. Based on what we've seen, most of the lazy vals in real code aren't actually accessed by many threads at a time. With lazy vals currently in Scala C, even after it's initialized, you're actually paying a price for accessing it, you're synchronizing. In Doty, in order for a lazy val to be thread safe, you need to opt in. You need to write @volatile, which you also do for normal fields. If you want normal field to be thread safe, you write volatile around it. We have a different implementation that actually allows you to access even both volatile and non-volatile fields faster. And it's actually can be seen on benchmarks that are lazy vals aggressive. As I said, we also have deprecations. Some of these deprecations are shared between us and Scala C. So for example, the syntax for procedures is being considered to be deprecated in Scala C. You can write such code, and by writing this, you explicitly mean that this function returns a unit. And this is called a procedure syntax in Scala C. Unlike this, in Doty, we require you to actually write explicit return type. And that's a moment when I want to step away and say, how do we handle such incompatible rewritings? We're going to give you a writing tool that's going to take your code, which compiles in Scala C, and make it compile under Doty. We'll try to this tool is most likely to be based on what Scala meta does, so it will maintain all of your annotations, all of your comments, all of your indentation. And we'll try to make sure that you're actually able to compile the resulting file in both Scala C and Doty, like in this example. The other deprecation that we're doing is delayed init. So how many of you actually know what delayed init is? Okay, some know. Okay, so that's a magical class in Scala standard library, that's a magical trait that if you extend, when you write something in the body of the class that extends delayed init, it's actually going to not make the body the actual body. It's going to make the body be a closure that's being passed to a function that I'm not sure that you know of existence. So let me illustrate this on this example. So if you're extending a delayed init and B your R class, it means that whatever the body of the class is should be passed as an anonymous closure to the method called delayed init, which is virtual, so you can override it. So in this particular case, the initialization of class C, just allocating it, will first print this dummy text, then it will actually start evaluating body. It's very unintuitive, because when you actually define the fields of a class, for example, if you here has been defining fields, methods, then you would expect it to actually be fields and methods. And Scala C does a lot of tricks to make it actually survive and not have bugs. We ended up on, because now we have a more general replacement for this, trait initializers. Now we have a general way to solve such problems. So if you really want to have some out-of-order execution and out-of-order initialization, you can actually pass it as an argument to a parent class or trait, as you were able to do it previously. So yeah, it just works, and it works in a normal way without requiring any magic from compiler or you to be aware of the tricks that it does. Okay, so those are the things that are currently implemented in Doty. There are some other stuff that we are considering that may or may not be part of Doty in future. For example, we're now trying to understand how should implicit search work, how should type inference work, and we also try to weight every of the decisions against how much is it going actually to break your code. We're trying to not break your code. Additionally, Doty has stuff that allows new possibilities and holds Scala ecosystem. So let me show you a problem that I had in my early days of Scala. So in my early days of Scala, I was using Play. And I was using some version of Play that depended on Scala 2.8. I was trying to make advantage of features of the new Scala 2.9, and it didn't work well. I had some issues of SBT, some exceptions being thrown, and it took me several days to actually find what's happening. Now SBT in such case actually reports a pretty good error. In case you're depending on the artifacts which are built by different versions of a compiler, it won't allow you to do it, because actual different versions of the artifacts compiled by different versions of Scala compiler aren't compatible with each other. And occasionally you have a lot of such questions being asked by different people on Stack Overflow, on Play. A lot of people once will meet this problem in the either did it in previous releases of Scala or the future ones. Actually, it's both a problem when you're trying to use the legacy code. So let's say your application depends on the legacy library, which is not going to be updated, and a library which is well maintained, and then the new library that's well maintained, you want to use a new version, and it depends on the new version of compiler, that's fine. But the legacy library is, well, nobody updates it, it's abandoned, but you still use its functionality. Then you're in a problem, because you can't actually use both of them at the same time, and you either need to decide not to use the legacy library or not to upgrade with a new library. So using legacy libraries currently or unmaintained libraries is hard in Scala. There's an opposite situation. Let's say you want to use some experimental feature which is developed in some experimental library that depends on the new fancy stuff in Scala 2.12, for example. For example, it depends on Java 8 streams. Well, once again, you have a problem. You cannot combine artifacts compiled by Scala 2.11 and 2.12 in the same class path. So it means that from library author perspective, you want to carefully decide what you depend on, because the more you depend on, the more you're restricting your users on what they can depend on. And, well, if you have a lot of users using different versions of compiler, you need to publish multiple versions to Sonotype. From the library user point of view, well, he needs to actually be really careful about what library does he use, because he'll going to depend on all the transitive dependencies on the libraries, and if one of those ever becomes, for example, unmaintained, well, he's going to have a slight problem. So I believe, and actually this problem is even harder. We now are going to have Java 8. Java 8 defines new bytecodes, which are, well, they're features, but they're incompatible with Java 6 and Java 7. And they're incompatible with Android. So if you want to use new fancy features of Scala 2.12, which work under Java 8, well, if you're a library, then see, people who are still willing to use it from Java 6 will have a hard time doing it. Additionally, we have a new backend. We have JavaScript. So if you want your library to be used from JavaScript, well, you need to publish it for JavaScript, or people need to compile it on their own for JavaScript. Actually, additionally, we have different forks of the compiler, which themselves are binary incompatible with the type-safe compiler. So in the end, currently, if you're a library developer, you need to consider publishing for all versions of compiler, 2.10, 2.11, maybe 2.12, for different versions of the backend, Java 6, Java 8, JavaScript, different forks of the compiler. And well, you know, when I needed to publish for 2 different targets, it was hardish. So I have my library Scalabliss, which is published for 2.10 and 2.11. I was able to make SBT working. But compiling for more than 6 targets, I believe it shouldn't happen. I mean, I want to live in society that doesn't have a constant headache. Okay, so I believe that this shouldn't bother neither developers of libraries nor users. They should just use the fancy stuff which is around, or the legacy stuff which still happens to work in your project. And well, in Doty we have a principal solution for this. So there is an idea of tasty, which stands for type ASTs, which was originally proposed by Scala Meta. So bytecode is too low level, as you've seen at the keynote talk yesterday. Scala C cannot actually get back the information from which it started to compile the code when it's already compiled down to bytecode. What we do instead is we define the interchange format, which we save additionally to the bytecode, from which we're able to recreate everything that we need, which includes the trees that are being compiled, its types, their positions for error reporting, and custom sections that can be used by other use cases, such as Scala matcher or linker that I will be talking later about. So the way it works is when you compile something by Doty, you can actually get a class file where inside you have encapsulated the bytecode and tasty. And if then you need to recompile by a different version of compiler, which, for example, has some bugs fixed or changed its internal ways how it compiles stuff, it doesn't need to actually be able to access the source. It is able to do it on demand without asking you for it. So I can actually demonstrate how this works on a small example. So let's say I have a class D here, which is being yeah, of course. So let's say I have class D here, object, which is being compiled by some crappy version of Doty, which has bugs. It happens. And the way it's going to work is I compile it with my version of Doty, and then I artificially make it wrong. So Doty, when it works correctly, it compiled two classes called, it compiled two classes called D dollar class and D dot class. One of the ways the Doty could be wrong is it forgot to compile object. So I just go and remove object. And that is definitely wrong. This shouldn't happen. Let me show you how Doty will be able to survive this. So I just take Doty and say that it needs to recreate the class from what it originally has. And then now what I see that this class exists. Doty was able to recreate it through the worst imaginable incompatible change that you can think of.
I assume that would have worked without the Scala file.
Yeah, I can delete it. So here is d.scala. I removed it, and I also remove d dollar, the class that I was speaking about. Here you have it. Ah, that's a different thing. Doty is currently not able to do it twice because it forgets to save the tasty once again. That's a bug actually. So you're able to do it only once. Yeah. Yeah, I mean, you should maintain the original. You shouldn't recompile it multiple times. So I'm kind of using it in an expected way here for demonstration. So let's say I compile it first time from Scala, from Doty. Then I remove the source, and I remove the class file. Or I remove all this stuff. Then I see .c.tasty, d. And here you are. Here you have this all d stuff. D dollar is here. And if you go into it and see how it looks like inside, here you have the bytecode. It's fine.
So is the tasty stuff stored in those mystical A1 things?
So tasty stuff is actually stored inside the class file. You have different sections which are defined by Java specification. You have a notion of attribute. For example, Scala C uses Scala C uses annotations to store top-level signatures because the signatures of Scala C are a lot more complex than one of Java. Doty uses attributes to store them. You can actually see it from, let me show you. You can actually see it from Java P. So if I take Java P and say that I want to see what's inside this class, you can see that here is some tasty attributes. Yeah, here it is. It's actually a very compact format. It takes somewhere like 30% of the bytecode. So it's more compact than the bytecode itself. before compression. We originally thought that it's going to be huge. We'll need to compress it, but when we thought that when we have seen that it's smaller than the bytecode, we didn't even bother with compression. Okay, so tasty allows you to get the source from the compiled class files. But when I'm telling you that's the source, I'm actually simplifying it a bit. It's the source after type checking. It's a source after inferencing type parameters, after implicit search, after all this stuff. It means that if we're going to change the way how implicit search, for example, works, which happens several times in history, we're not going to break already existing tasty files. We're more than binary compatible, and we're more than source compatible. And tasty also allows you not to publish multiple artifacts to Maven. You just publish something which is tasty, and then if somebody needs to use it in Java 6, it's going to compile it for Java 6. Somebody needs to use it on JavaScript, it potentially can compile to JavaScript. That's an ideological thing that we believe will work. But currently, the only thing that's actually is implemented is going from Java 8 back to Java 8. Yeah. Okay, so additionally, this opens huge possibilities for Scala Meta. It means that Scala Meta will be able to see what was the original source of the particular file. How was it written? What was inside? What were the fields? What were the internal variables? This opens entirely new possibilities for metaprogramming that Scala Meta is going to provide for Doty. So in Doty, you're not going to have current Scala reflect macros. At least we don't believe that we will be able to implement it. Instead, we rely on Scala Meta to provide us metaprogramming.
Sorry, one question.
Yeah.
Is it going to be forwards compatible as well as backwards?
The notion here of compatibility is funny because it somehow relies on the format that we store. So as of now, this format is very extensible. The format that we have now and the scope in which Doty uses us now is currently both forward and backward compatible because the changes that were introduced are gradual. But you're able to extend it with new sections. And that's intended. Because, for example, Scala Meta is going to save its own information about where the comments were. Tasty doesn't maintain the comments, for example. And they need to be stored separately. And that will be a question for all the projects that actually utilize custom sections to say what's their compatibility approaches.
Because you would get into an issue where somebody publishes a jar for a future version of Scala, and you're still on the last version, and you can't use their library now.
So the versioning of Tasty is independent. Tasty has its own version. So if you have a new version of Scala compiler that didn't change the version of Tasty, you should be able to support everything. Additionally, there is a string inside that tells the full name of the compiler that compiled that thing. And if you have some invalid Tasty somewhere around, you know who to blame. Okay. Well, unless somebody was intentionally not saving his name. Okay, so now I'm going to say a bit about my project, my interest in Doty. My previous project was Scala Blitz. In Scala Blitz, I implemented with Alex Prokopets, I implemented operations for Scala collections, which were able to give ridiculous speedups in some cases, or in general reduce pressure on garbage collector. So for example, for the case when you actually summon numbers inside arrays, we're able to get speedups like 100 times. We get it by not creating garbage, not creating closures, not boxing arguments, and by doing this, we're able to get better memory locality and CPU throughput utilization. When working on it, I actually understood that the approaches that we were taking there aren't specific to Scala library, the Scala standard library. They're not specific to Scala collections. They can be used for arbitrary library. So what I'm working on now is something called linker. Linker takes tasties of all of your dependencies, takes your application, and tries hard to tune the library to fit you the best way possible. For example, if libraries have some features that you're not going to ever use, it's going to remove them entirely. Or if you're using the library, for example, you have a general collection library that's able to work on vectors of whatever, but you're using it only for vectors of integers. Well, it will generate a specialized version of integers, vector of integers for you. That's the only thing that you need. So, for example, by doing this, it's able to survive the exponential explosion of specialization. So, for example, in Scala C, function 4 is not specialized because you'll need to create ridiculous number of classes to do it. It will just fill all your file system. But in real programs, you don't actually see a lot of function 4s. You need only some of them, but the ones that you need are specific to your program. And by using linker, you can actually get the most that you can get from the libraries and from the whole ecosystem. But when doing it, it actually removes your dependency on the library. It somehow incorporates the libraries inside you. So you can think of this as something like smart ProGuard or smart way to build a mega jar out of your library which doesn't have external dependencies. If you're interested in there are 2 links here where I'm speaking about this in Scala Days Amsterdam. Additionally, one more important thing that we care about. So in Doty has substantial different internal design. While designing Doty, we were caring about how it would perform in terms of speed. We didn't actually do a thing while trying to tune performance by hand. But even now, we're already on more or less on par on compilation speed with Scala C, which was doing huge steps to try to be fast and was improving in latest versions. Okay, so now I'm going to go for the second part, and I propose if you have some questions about Doty in general, I propose you ask them now, because hairy things and scary things are going to start now. Okay, yes, please.
Just one question about going way back when you said you decided to change lazy vals not to be thread safe.
Yeah.
Other than via the volatile annotation.
Yes.
That feels really counterintuitive. That's certainly, if I see a val,
yeah,
I don't expect it not to be thread safe, whether it's lazy or not. So it feels like that might violate the principle of least surprise. So it feels like that in an application you're likely to have multiple threads, so you're likely to just stick the volatile annotation on it all of the time, just to be pretty confident that you're not going to have problems. So why did you take that decision? So
first of all, if you have a val, you're not guaranteed that it's thread safe. For example, if you start a thread inside constructor, and this thread is going to access this field, you don't have any guarantees on what it's going to see. So you shouldn't rely on vals in Scala C being thread safe just because they're vals. You should take some different steps. For example, make sure that you don't have if you actually have a real memory barrier before you access it. One of the memory barriers by Java specification is end of constructor. So as I told, we have the rewriting tool. What the rewriting tool does for lazy vals, it's for all lazy vals and Cs that come from Scala 2, it will just snap volatile element. So it's going to maintain semantics of your code. To speak more about the internal stuff, actually inner objects in Scala C and in Doty are implemented as volatile, as lazy vals. So if you write objects, it's actually going to be thread safe by default. For objects, you're not we don't provide you opt-in to be not thread safe. But for vals, well, that's decision that we needed to take looking at the ways how lazy vals are used inside Doty, inside Scala C, inside standard library, and several libraries that we considered.
I guess my point was just that as a user of this,
yeah,
when do you think your users are going to be so confident that they couldn't possibly have a lazy val being hit by a different thread, that they are so confident that they're not going to use the volatile annotation? It just feels like if I was using this, I will always use the volatile annotation.
Yeah, if you're fine with paying, so the question was, because if you have non-volatile lazy vals, you have less guarantees. So if you're not sure that it's not going to be accessed by multiple threads at the same time, why don't I always just snap volatile on it? When you say that's a volatile lazy val, you're going to pay the price of accesses for it. Accessing it, it's going to be slower. If you want correctness, indeed, you can just snap volatile everywhere. But if you care about performance, well, we already have several cases where people start re-implementing lazy vals because they want less guarantees but want to be faster. And in many cases, they're doing it wrong. And we want a general provided solution for this problem.
It should probably be noted that in almost all cases, lazy vals cache a computation that is usually not side effecting, and they are just an optimization where the race of doing it twice is benign, and that is the reason why it is beneficial to not have these extraneous barriers in this case.
Yeah, that's true. Yeah, that's true. So, okay.
Oh, sorry, if you're going to continue answering, I wanted to continue on the volatile thing as well.
Yeah, of course.
All right, so I was going to say two things. One is that even with Dotty, you don't actually have to make it volatile, even if you're hitting it with multiple threads. If you're sure that you're passing through some memory barrier somewhere else,
that's true.
That after the value has been written. So for reads, for example, if you're reading it concurrently in multiple threads, but you know it's already been initialized by the time you get there, which actually is an enormously common case, then it's completely okay for it to be non-volatile. This is the same case where we make vals non-volatile in Scala in multi-threaded use cases, which is in fact, most of the time. So I think it's a good trade-off overall. Like I think it's good to kind of force that to be annotated.
So if you don't mind, I'll repeat for the recording. So to repeat Daniel's Spivak, were they you?
Yes.
Yeah. So Daniel Spivak tells that it's a more common use case when you actually have multi-threaded access, which happens after you already have some guarantee that the lazy valve was already initialized. So the only part of lazy valve which here will be unguarded is the initialization. And then if you know that, for the common case when I use lazy valve is when I don't want to bother solving the initialization order when I have multiple trades being extended. In this particular case, I know that by the time object is being finally constructed, all of them are actually initialized. And in this case, I'm not going to pay, I won't pay the price of accessing them. Okay, so do we have any questions left about high-level view of Doty, or are we going to guide? Okay, please.
I've noticed in your overview you're not going to discuss the presentation compiler.
Yeah, so for now, the Doty design is just a simple compiler that is not going to try and, let's say, implement all the stuff that previous compiler was doing. We want presentation compiler to be one of the potential usages of our API. So there can be multiple implementations of presentation compiler, and we want our API to be pretty general that they can improve on their own. There are some stuff that's needed for, let's say, IDEs, like targeted type checking. It's in early development stage. We don't prioritize it just yet, but we intend to have it.
You will have it, okay.
Yeah. Okay. And so that's one of the improvements why we believe where Doty can actually bring a lot of stuff, because given faster type checking time and faster compilation time, I believe we can improve users' experience in IDEs. Yeah. Yes, please, questions?
Are you going to show a slide somewhere which will tell me how I can go and play with this stuff?
Yeah, I can actually show it now. So what you do is you go to the GitHub repo, of Doty, you check it out, you say git clone this, then you get a repo like I have here. Oh, thanks for telling. Here you have a bin script, .c, and you just use it, that's all. The first time you'll use it, it will actually compile Doty. Using SBT, it will download all the dependencies and all that stuff. As far as I know, it works on both Linux and Mac. I have some reports that it works on Windows, but I didn't check. Yeah, and if it doesn't work on Windows, feel free to contribute. Okay. Yeah. So the status in which Doty is now, it compiles itself, but the result doesn't run. We've already passed through a moment where we're finding simple bugs. We're now trying to find complicated bugs to stop us from being compiled. We're all the time in the same situation where it looks like that's the last bug we need to fix, and we're going to bootstrap ourselves. We're in this state for 4 months already. Yeah. And actually, by fixing all these bugs, I now have a really good understanding how Scala actually works, and all the artifacts, and some fun stuff about how Scala C works, but I will talk about this in the next slides. Yes, please?
Okay, so you showed this slide about tasty, and as far as I understand, you already deduplicate com terms and type names.
Yes.
To get the file size down.
Yes.
Did you try to, instead of storing those com names in tasty, just referring to the constant group?
So the question is, Tasty already does some deduplications. If you're referring to the very same type or the very same term several times in Tasty, it's going to actually reuse the reference, and that's why it's so small. It doesn't repeat itself that much as a bytecode does. And the question is, we can actually make it even smaller by also referring to the constant port of the Java bytecode. Yes, that's true, we can actually do it, but as of now, Tasty is already really small, so we'll prioritize in different stuff. If one day we'll need to make it smaller, we can introduce this feature. The first feature I will actually introduce if we ever needed to make it smaller. I will use some on-the-fly compression, which is fast, because it's really easy to add, and it's not zero effort. But for now, it's already small. Yeah. Actually, if you compare the bytecode generated by current Scala C release versus the bytecode generated by Doty, Doty is going to be smaller just because it uses Java 8 lambdas, and by doing it, it saves on the bytecode size. So even though we create this Tasty section which takes place, it's still better than the current stable situation in Scala C. 2.12 is also going to use lambda meta factories and Java 8 lambdas. We actually share a lot of this implementation. We look at each other and look how it works on both of us. And actually, the encoding of traits that's going to be in 2.12 is inspired by encoding of traits in Doty. So yeah. Yes, please?
Okay, so you showed the inference of singleton types, which works by default.
Yeah.
If I don't want singleton types to be inferred, then how would I do that? Because I think in Scala it's just other way around, but it was proposed to be just other way around.
So. Yeah, so the question is, here in the example I showed with singleton type, the type that was inferred here was 2. Actually, so the question is when do the question on precise typeness. So how much precise do the type that you how much precise do you want the type that is inferred by a typer to be? It's a general question here. So here I actually explicitly told Doty that I'm going to have 2 here. Please try hard to infer it, because that's the expected type. As far as I know of now, if I move the 2 here, it's not going to infer singleton type. Yeah. So currently it's not inferring a lot here in this particular example. It's just type checking mostly. It's not that aggressive in inferring those types if you don't ask it for it, because in some cases you can get unexpected results with them. Okay, so any questions left about this part? Okay, let's go for the hairy stuff. Okay, hairy stuff starts now. So here's the plan. I'll talk a bit about Doty internals. First of all, Doty is not a cake, unlike Scala C. And I will show you several examples why. I will also show you that Doty doesn't have global mutable state as Scala C has. And then I'll talk about the notations that we have, and they're actually a replacement for Scala C symbols, more or less, and why we needed something that is more expressible than Scala C symbols. Then I'll talk about denotation transformers, which actually allow you to, given all denotations, create new denotations. And in the end, I'll talk about mini-phases. That actually is one of the major reasons why we're fast by design. Okay, so Scala C is a big cake. And by cake, I mean that most of the parts of Scala compiler actually say that they're going to be combined in the Scala compiler. They're aware of it while type checking. Let me show you a small example. Presentation mode here. So global is what actually a Scala compiler is. So that's the main part of Scala C. If you'll have a look how it looks like, it actually mixes in some stuff. And if you look at the phases, phases themselves are part of mixin. So the mixin somehow injects itself inside a phase. And funnier, if you know what early initializer is, it does it before the constructor had run. There's quite dark magic happening here. If you actually dig a bit deeper, for example, go here and here, you will see, okay. So given this, I have several questions that I have to ask every time I'm thinking about doing something in Scala C. Let's say I have something written in Scala C. I want to know where it is used. There is a huge scope that I need to consider here. IntelliJ does help me somehow here, but it actually occasionally fails because it's really complicated to see where this stuff can actually be seen from. Okay, additionally, if I try typing somewhere and I wait for IDE to tell me what are the potential, well, how can I end up my comment or a command, it's going to give me hundreds of possibilities. Miles, do you have a question? Or, yeah, I can hardly see from here. So this creates a huge namespace pollution. So if you're thinking about a good identifier for some stuff, it's very likely that there is another place in compiler with this identifier also makes sense, and this identifier is already taken. Well, let's say that you want to introduce a new method, some utility method that you believe is going to be commonly used. There are a lot of places where you can actually introduce it in Scala compiler. And that's the same problem with when you're looking for something. There are multiple places that you better check, because it's not obvious where the stuff is, because everything depends on everything and it sees everything. It actually doesn't matter from compiler point of view where you put stuff. Yeah. And if you actually try to extract some parts from Scala compiler, it's really hard. So for example, Eugene did marvelous job trying to extract parser from Scala C. As for somebody that knowledgeable from compiler as Eugene, as far as I know, it took some substantial time, like a week or so, of just doing only this. So yeah, unlike this, Doty is not a cake at all. Instead, Doty has several small cookies inside. So let me show you several cookies that Doty has. One is context, which I will speak about a bit later. So that's all it has, it's context. If I'll show you symbols, well, symbols, no surprise here, it's something that is just a context, nothing else. And the same as everything here, so well, reporting, well, it's just a context, no magic. Actually, context is really small. And the context is actually what encapsulates mutable states inside Doty compiler. Same with typer. So in Scala C, typer is a huge monster. In Doty, well, it actually is, but it's, I would say, better contained. So for example, there is a thing called type assigner that tells actually how do you assign types, not how you infer it. And, well, it doesn't depend on anything. It's just a type assigner. It doesn't need to know that it's part of Doty at all. So you can just take it and use it in your project by assigning types or what. Okay, so, and the same with all the classes. Pattern matcher is also a cake, but a smallish one. Gen B code is a cake, but a smallish one. Okay, so Scala C. Scala C has a mutable state. So because everything is a cake, everything is able to interact with everything. If you want to actually do something, you need to change the state which is floating around. Given this, let's say that you want to implement something like this. You're going to try possibilities. So you want to try and do something, and if it fails, roll back and try something else. You can actually do this in Scala C, but the implementation is really enormously hard. The way it works in Doty is everything that exists in Doty takes a context. All the immutable state is in context. Symbol table is in context. All the constraints that typer inferred are in context. If you want to try an experiment, you just make a fresh context out of the one that you have, experiment with it, or it failed, so nothing breaks. Yeah. So in Doty, everything takes a context. No global states, nothing. Symbols. What's wrong with Scala C symbols? If you were at the talk that was yesterday about diving into Scala C, it was said that symbols are a result of name resolution inside compiler. So let's say you have a class C, and you want to know what's something called foo in class C. And you say that's a method which, here it is. The problem is that this definition is just flawed. The question, what is named foo in this particular class, depends on when do you ask. The members of the class change substantially between typer, eraser, flatten. All this stuff moves around, members are introduced, members are moved, they change their types. So if you're going to go with symbols, well, you have a problem that you don't know whether it's still valid, when was it valid, and all this stuff. So we actually have denotations. Denotations say this is the meaning of this particular name, the meaning of this symbol in this particular period. By period, I mean this particular compilation phase. And they actually form a circular list. So if you want to know what's the future of this particular denotation, where did it go, how did it change its type, maybe it's entirely disappeared, you just follow the linked list. You all can also just follow this linked list to see the first meaning. So some of the symbols don't exist by typer, and you can actually see that the first valid denotation was after typer. This also allows to have all the versioning of full info of the symbols. So you have the type, the name, the flags in any arbitrary phase inside compiler. And you're able to actually travel back and forth inside compiler and ask those questions. Is there a question somewhere? I mean, I can hardly see the audience from here. Sorry. Okay. So just to demonstrate it, let's say we have a class C, which has a member ID inside, and we're going to compile it. Actually, both Doty and Scala have a lot of phases. I will simplify the situation and say, let's say that we have only 3 phases. And let's see how the representation of this class changes. So I start with showing how the representation of the inner method ID changes. The biggest thing to change the meaning of ID is erasure. Before erasure, you had the full Scala type system, so it was method which was polymorphic, and it was taking T and returning a T. After erasure, well, it takes an object and returns an object. And those denotations form a cycle, and every other denotation knows where it's valid. A context actually knows when is your phase when you're asking a question. If you're going to look at a denotation, you're going to do it with a context. And this denotation is going to actually update its meaning and return you the valid stuff. So you're never going to see something which is out of date. Actually, on this picture it looks easy, but even if we consider 3 phases, it's actually not that simple at all. So, as I told you, the ID changed its meaning in erasure. Around this we actually have the packaging which is defined. By default you define everything package empty. The class also changes its meaning on erasure because there are a lot of stuff happening around. Well, I don't want to go into details in this. But additionally, the thing that happens is that, for example, object C starts to exist during the first transform. So it means that the meaning of the package should have changed because it got new members. And then let's say that you're currently at the phase first transform, this vertical phase, and you're asking class C what's its parent. Well, class C was originating from this phase, which is typer, and it's going to say return you the denotation which represents the package on typer. But as soon as you're going to ask it something, it's going to go to see that you're asking it about the first transform. So it will silently go through this link, and you won't see invalid data. If you want, you can explicitly go to a specific phase through context by creating a context with a changed phase. Once again, you're not changing any global state. You're just creating a context which is working on a different period, and you can ask arbitrary questions to compiler. Yeah. Okay. So in order to implement it, we have the notion of denotation transformers. So denotation transformers take a meaning of a denotation on one phase and introduce a meaning of the denotation in the next phase. So for example, erasure takes members and starts erasing them, creating new meanings for them. That's something that doesn't exist in Scala C, and it actually also contributes to us being fast. This allows us to make transformation of types and members lazy. If you're not using something, well, the denotation is never going to update its meaning. It's never going to lazily invoke this denotation transformers. And this helps a lot in being fast because you don't actually need to eagerly go through all the members and compute stuff that you would never need. Okay, the next phase at country. Is there a question there?
Yes.
Yeah.
So how does the phase travel work in Doty? Like you have in Scala, see the entering type or entering erasure stuff. Is it like what are the differences computationally from memory perspective?
So when you're traveling, the only thing that you do is so this phase is part of the cake of the context. So you take a context, so val as.context, and what you do is you create a new context based on it, context at phase, and here say what phase. So for example, as.type per phase. That's the thing that you asked. Here you get a new context, and here you do what you wanted. So, yeah.
So if it hasn't been asked before, it hasn't been computed yet.
Yes, it's going to invoke this denotation transformers.
Okay, and so after you did it, it's basically lazily computed. If you would do the same.
Yeah, you will get the same result.
If you do the same query also in like another file or in a different phrase, then it would still wouldn't still recompute anything.
So if in the same compilation run you have the meaning of notation computed, it won't recompute it once again. It remembers it. They form this circular list that you're able to travel in one direction. So when you actually need to travel back, it actually just makes the full cycle. Yes, please?
So one of the biggest problems I've had with symbols working in Scala macros is that, I mean, typically when you're running macros, symbol isn't actually what you want. You want something as simple as a prefix. And it seems to be very unclear in lots of contexts how you, I mean, there are many APIs that will give you a symbol but won't necessarily give you the prefix that you need to actually use it in a particular context. And I've had innumerable problems sort of stitching prefixes back to symbols. I'm reasonably convinced that most existing Scala macro code out there is broken. It doesn't actually do this kind of stuff. What's going on in denotations that helps me with that?
So first of all, so the question was, if you trying to look for something in Scala macros, you're doing it in a type pair. Symbol is not always what you want because it doesn't have actual all the expressiveness, and you don't always know where to look for the symbol. What would be the prefix of the place that you're looking for? Am I getting the question right?
Well, I mean the dependent path prefix. That essentially determines a combination of a prefix and a symbol.
So denotation is not a type, to be clear.
Sure.
Denotation makes a meaning of a type. If you're talking about dependent paths, then you're more interested in types. Types themselves start creating denotations, and denotations, they create meaning of the types. So if you want to actually look for some member, then Doty has a real strong self-checking framework that ensures that everything is in a specific place where it's expected to be. So in Doty, you shouldn't have surprises on where you're looking for stuff. It should be in specific places, and we're actually checking that it is. The test suite actually does a lot of checking, making sure that nothing goes wild. And then you have a pretty specific place where to look for, and you can use term refs, which is a type, and type refs, which is also a type, and ask it for denotation. It could be a multi-denotation, which means it's overloaded. Yeah, you can do all of this and it should be stable. Yeah. Yes, Eugene, please?
So I would like to clarify that to the best of my knowledge, Doty's denotations, they don't carry prefixes. So I guess this is what you were asking.
Well, I guess, so does that mean I would still have the problems I currently have with Doty?
Well, unless you use Scala meta, of course.
So the most denotation that you care about are sim denotations. I can show you what it actually has, if the IntelliJ helps me. So here is sim denotation, object sim. Yeah, so here it doesn't actually bear a prefix. If you're interested in speaking about prefixes, you're in the types area. Okay, any questions? Okay. So now macrophases in microphases. So let's first have a glimpse of how the phases work in Scala C. In Scala C, phase is something which takes a whole compilation tree, all of your code, and does stuff to it. It can do whatever it wants, it can just throw it away, just walk around it randomly, replace nodes, shuffle them around, and do whatever it wants. It means that the phase in general actually follows all the tree because it needs to find something that's going to transform, tries to find it, rebuilds it, makes the changes, and rebuilds the tree, including the changes that it wanted. In these images, I will use colors to represent different AST nodes created by different phases. So we start with the blue trees, and then we have a yellow phase which just goes around, changes the tree, and marks them yellow. If we have several phases, so if we have 3 phases, we'll have 3 traversals of the tree, 3 rebuildings, and because all of these rebuildings in most cases take time because the trees are huge, by the time you finish rebuilding it, you've created a lot of garbage, you've created a lot of objects, and actually your tree is already in old generation. So you've created a lot of stuff, and there's actually a place for improvement here. So to summarize, macrophases traverse the tree independently. Because they traverse it after each other, they actually in most cases are reading cold data, because they are polluting each other's view. They create new subtrees independently and need to rebuild the tree from scratch. And because it takes time to do so, actually those trees are promoted to old generation. So the other question is, because it works this way, you don't want to have a lot of phases, because you're going to be slow. Every phase means go there, look for all the trees, find what you want, and make small rewriting, and then huge rebuilding. Because of this, I have a funny question to ask for you. So, do you know what phase actually implements lazy vals? I have a hint for you. There is a phase called lazy vals in Scala C. So, that's a state in Scala C. You have a lot of phases here, and the phase which implements lazy vals for objects is mixin. Fun.
We're fixing out is 212.
How is this going to be called now?
Lazy vals.
Okay. Okay. What is super accessors going to do in 212?
Super accessors.
Yeah? And anything else?
Hopefully not.
So as far as I know, as of now, super accessors has around 80 lines which do super accessors and around 700 lines which do stuff.
Yeah.
So, so the problem is, if you try to be modular, if you try to make self-contained small parts, small phases, that just do the thing that they're intended to, you're slow. Because you'll have lots of them, and you'll spend most of the time just by traversing the tree and rebuilding it. To solve this problem, in Scala C, multiple functionalities that are ideologically independent were merged. So multiple phases do something additionally to whatever they say. What's unlike this, in Doty, we have substantially different strategy. We restrict phases. They are not allowed anymore to define their own traversal. They don't define in which order do they see nodes. Instead, we say that all the phases see the trees from leaves to root in the order in which they are more or less defined by user. It means that all the phases first see the definition of something, and then we'll see the usage. And as we see, most of the phases can actually be implemented given these restrictions. But the fun part is that then we can start rebuilding the tree incrementally. We don't need to rebuild the tree entirely. So let me demonstrate it for you. So let's say we start with the same blue tree. We take single node, which is the leaf, and transform it with a yellow phase. Then we're not going to rebuild the whole tree. We're going to just apply green phase to this node. And then we're going to apply orange phase. And then we're going to rebuild something like this, which is, we're not actually going to rebuild it, we'll assume that this somehow existed. And now we're going to recreate this node with new child and make it actually follow the same transformation as the previous one. So what we did here is all these green nodes, all these yellow nodes now live for a really short period of time. They die young. And in most cases, when this green phase does something, well, it does it to a yellow node. The data is hot. It's able to access it fast. And when it creates something, it doesn't introduce garbage. Based on this, in Doty, we're allowed to create mini-phases almost for free. So in Scala C, as we have seen, we have somewhere like 25 phases. Let me show you a number of phases in Doty. So they start here from line 40 and they end here in line 87. So we have 47 phases. And we can actually add them almost for free because they don't create new garbage which lives forever. They don't create misses in the caches. And it's fast. And we didn't do anything for it to be that fast. It just happens to be fast because we designed it this way. Yeah, so I'm somehow proud of me coming up with this microphase. I guess it's pretty obvious. Yeah. So
I have a question.
Yeah.
It's very clever, and clearly a very, very large percentage of the transformations that we would want to perform in not just Doty, but most compilers actually could kind of fit in this model between this and denotational transformers. But I guess the question I would have is, I can envision some transformations that I would want to perform in a compiler phase that sort of touch more broadly across the tree.
Okay.
That perhaps wouldn't fit into one of these sort of metaphorical boxes. Is it possible to define those phases still?
Okay, so the question is, here I'm making some restrictions, and the question is it possible to define the phases which don't follow those restrictions and don't fit into the scheme? So first of all, yes, we have a notion of a phase still, that you can create a phase which does stuff, but you're not advised to do so.
Right.
In most cases, what I have seen is if we write a phase, it's not always obvious how do you rewrite it as a mini-phase, but if you think more, you actually come up with a way how to structure it better, how to understand it better, and make it actually even smaller, know how many lines of code does it take while making it mini-phase. Additional thing that you actually have a lot of guarantees here. One of the guarantees that I spoke of is that you always know that you first will see a definition, then you will see all the usages. It actually handles most of the cases. One more thing, that's a lot of cases when you need to know some non-local stuff, you can actually extract it from types. So in my experience, there are not that many cases that don't fit into this framework. And some of the cases when we actually implemented something which is not a mini-phase, we did just because it was faster and we wanted to bootstrap faster. I still have discussions with Martin and I'm trying to convince him to make erasure a mini-phase. I'm willing to try, but honestly, I don't have time. I need to bootstrap Doty first. But that's something that I'm doing in my spare time, more or less. Yeah, one less typer in Scala, in Doty. Yeah, so erasure currently is full-blown typer, which is a megamorphic, mega phase in all the senses you can imagine. Yes, please?
Is it possible to force individual mini-phases? From my point of view, it looks like a nightmare to debug if there's some wrong AST transformation going on in the middle of such a mini-phase, in the middle of multiple mini-phases.
Yeah. So the question is, in case something here goes wrong in the middle of the mini-phases, it's actually hard. It could be hard to debug it. Well, if something goes wrong, then you can actually make every mini-phase be a full-blown phase, because they will just run in isolation from each other, and you will be able to test it. Additionally, lots of checks can be actually seen from types, because most of the phases in Doty actually are denotation transformer and a mini-phase. And then if something goes wrong, it's pretty obvious what it is. But indeed, in some cases, as always in compilers, it takes days to find what's wrong. Yeah. So I will also speak about the checking that we have there in several slides, or like now, and I will actually show you the checking framework that we have. So, any questions about mini-phases? Yeah, checking. Well, developer compiler is hard, and if you want to rely on something as compiler, maintaining some invariance in compiler is enormously hard. For example, Scala C is known to break owner chains in all the ridiculous ways you can imagine. Or Scala C is known that you cannot just take a random tree inside the pipeline and retype it, because it's ill typed. Unlike this, in Doty, all our test suite, all our integration tests check that for every test in the test suite, you can actually retype the tree after every phase. That all the types are correct after that the owner chains are the same that are expected, that they don't get broken, they don't have any unexpected stuff like double definitions or stuff which is undefined. If companions were there, they don't disappear suddenly, like in flat and in Scala C. Yeah, that you additionally don't create any invalid names. For example, which was fun for me, that on GVM you can have variables which start, variable names which start from last symbol. But you cannot have methods which start from last symbol except constructor. So this while checking infrastructure checks all of this invariance. And additionally, every phase, every mini-phase, it's able to add its own post-conditions. So for example, after pattern matching has run, there shouldn't be pattern matches. After erasure has run, there shouldn't be unerased types. And it means that a good phase will not only do its job, but it additionally will define a way to check that it's done its job right. So just to show example of how it works is I have a custom phase here, which originally I wanted to go with for the workshop, but then I went for the presentation. And I'm going to introduce a bug here. So I'll take a class that's what I was intending to do. So what this phase is intended to do is to take options, which class like an option, optional, and make it never be boxed. Just always you have an option, you split it into two fields, one which is underline and one which is the boolean which tells whether the thing is defined, whether it's some or none. And we'll do it for argument lists, for fields, everywhere. So let me show you how it works. So I take this t1.scala, which takes an optional of int, and I compile it. Yeah, I had some modification to Doty. As I told, this dotc script is a bit smartish. If it sees changes, it's going to rebuild it. Yeah, just some changes, incremental. Yeah. So while it's compiling, let me show you several examples. So this phase defines a denote transformer, the indentation transformer, which for every method, if this method itself takes an option, we'll create one more method nearby it, which takes unboxed option. So that's how it's implemented. Additionally, it has a transformation of a tree, which transforms defs, and for every actual tree which was defined in a method, taking an option, it makes two methods. One which works on unboxed options, and the method that was there, which just forwards to this one. And here you have structure, which actually tells you of what transforms what in what way. So it's a lot easier for me to read this than in Scala C. Phases.scala. I've added stuff here. Is it going to rebuild everything now once again? Yes. Makes sense. I love makes sense. So to continue on the checking. So here this phase defines check post condition that checks that for every method that takes an option, there actually is a method that takes an unboxed option. And by doing it, it checks that it's actually done its job right. In Mini-Phases framework, it actually makes sense because you have this funny happens before questions, because, for example, let's say one phase just took a tree and stole it, just entirely removed it, and just waited for half of the pipeline to go and place it somewhere else. Then this tree is not going to be transformed by all the phases which were in the middle. And you should better be warned that somebody is doing some bad stuff here. It's not that optional did its bad job. Somebody was breaking the guarantees that the optional was providing. Or for example, you don't want somebody after erasure to synthesize the trees which have unraised types. If somebody is doing it, he's doing it wrong. Okay, so now have this T1. Let me show you how the code looks like. As in Scala, C would support similar options. So that's what I told you. We have this do stuff, which was taken optional, which was boxed. And now we have do stuff unbox, which takes an unbox optional and does it with all the stuff that the previous was doing without boxing. So the original code was we have a lot of phases like this. So if B is empty, undefined, else print b.get. Here we have if B is undefined, println in.box of b underscore. Yeah, because println expects an object. So we still need to box it here. I'm going to introduce a bug here. One of the really hard bugs to find in Scala C is the question, when do you introduce a member, or how many times do you introduce it? Let's say that somewhere here, for no good reason, I'm going to make actually this symbol be part of some scope. So I say that it enters a scope of current context. Obviously, I'm doing some random stuff here. It shouldn't work. Let's check if it works. Well, it does. The question is why. And the answer is simple. Checking all the tree takes time. If we'll do it all the tree checking on your machine, you're going to have slow compilation times. We want to have the most comprehensible checks possible and not make you pay for it. So if you want to actually check stuff, you do this. Why check all? And well, it exploded, as expected. So method.stuff unbox is already defined. Yeah, pretty valid error. I did something wrong. So yeah, that's how tree checkers work. How much time do I have left? 10 minutes. Okay, 10 minutes. Okay. So yeah, so we have a huge checking framework that ensures that all the compilation pipeline actually works in the way we expect it to work and doesn't give us surprises. Yeah. So the examples of post conditions that I already told you, and one of the funny ones that actually, so most of the post conditions are created after we've seen a test for which original implementation was doing something wrong. So the last post condition that I created was in expand private, that private members shouldn't override public ones. You can't actually write it in Java or Scala, but well, compiler can synthesize it on its own. And for example, in Scala C, till the very end of the pipeline, you have private members overriding public ones. And backend, if it sees this, does some very dark magic to try and fix it in ad hoc ways. In Doty, we check that it actually never happens, because that's a phase which ensures that this shouldn't happen. And that's actually a question when I was asking yesterday when there was a talk about Scala C on when do you decide to put stuff in the backend or where. In Doty, it's pretty simple, so expand private. That's a very small phase that has, well, actually like 30 lines of actual code, which does a simple thing, which is self-contained, which is not mixed with all the stuff, and well, it has some documentation on what it does. So you don't expect lazy vals to be implemented by mixing in Scala. So it's simply in Doty, it's implemented by lazy vals. And well, to be more explicit about it, the thing which is actually called and implements mixing in Scala C is like 10 phases in Doty. So to be honest, the stuff implemented in Scala C by mixin is this mixin plus memoize plus links to Scala classes plus some functional interfaces. There are several phases. We extracted self-contained functionality and made it isolated, made it testable, made it verified, and it's easy to maintain by doing this. Yeah. So okay, that's what I have as slides. Thank you for listening. Yeah. If you have any questions, I propose you ask them now. If not, I can actually give you a small description of how the Doty code base is organized, so you can play around with it and hack with it. Yeah, please the question?
So in Scala C right now, just kind of for relatively historical reasons, the parser does a lot of this very not self-contained stuff.
Yeah.
You know, handling for comprehensions and shelling out to Scala XML and other terrible things. And is that improved in Doty?
So the question is, Scala C is known for having parser do some stuff. It not only parses, but as many phases in Scala C, it does some desugarings, and because the parser is the first thing to run, you can actually hardly find how did the original source look like. In Doty, desugaring is done by desugaring, which is which is a self-contained thing. Here you have object desugar that has functionality that, well, you can reuse. So for example, this derived param tree, it's a case when, let's say that you have a type member inside a class which overrides a type member which is parameter of a class, and then in unapply in Scala C you have the unapply being in ill type in the middle. Because the way the desugaring was done, it was done too early, and it just copied over in the syntax level, and it's wrong. So we have a lot of functionality here that you can reuse, and it's self-contained. So for example, this is how the defs are being desugared. So for example, here the evidence params of use are being desugared. It's not even parser. Actually, when it's done, its typer goes for a tree and asks it if it was already desugared or not. It's desugared in a lazy manner here, to be honest. Yeah. Yes, please?
Does Doty fix SI 2712?
I'm not that knowledgeable in Scala issues, to be honest. We have our own bug tracker. Scala issues. SI?
2712.
2712. Let's try. I mean, for such issues which have a simple test case, it's quite easy to check.
Can you expand the font size?
Yeah, well.
Keep it this size.
It's okay. Yeah, so I was wandering around in editor. Yeah, it doesn't type this.
How do you like that error message?
Yeah.
That's really sad.
one dragon at a time.
So yeah, it says that there is actually implicit conversion which could be applied. I don't know. I didn't actually have a look at the test to know whether it should compile or not. Yeah. So Doty actually fixes some bugs. For example, Doty has pattern matcher substantially rewritten. And for example, well, in Scala C, pattern matching, which is synthesized by compiler, is based on options. In Doty, is based by what's called by name. Name-based pattern matching. So pattern matching over case classes in Doty doesn't create options. And it does it in a way which is compatible with the way how you would expect it to work, not by magic. So in Scala C, it neither does create options, but it doesn't follow the spec, it does magic. The other examples is that, so name-based pattern matching on product 1 works. You have value classes over value classes over value classes over value classes, nest them as much as you want. And pattern match it over that works. Yeah, such stuff. Any more questions? Yes, please.
You've not mentioned the parallelizability. Is it parallelizable, or are parts of the compilation parallelizable?
Okay, so the question is it parallelizable or are parts of compilation parallelizable? So when I was talking about these mini-phases, actually here you have the possibility to make those pipelines be executed by different threads. I played around with this. It doesn't make much sense because it creates a lot of coupling between threads. They need to exchange data too fast. You have bad locality. It's not worth it. From what we tried, the thing that actually makes sense is compiling different compilation units on different threads. It's actually the same thing which is tried by Scala C. It's a good thing, it works, and it's pretty reliable. In our case, we have this lazy denotation transformation that actually helps here also a lot. As of now, we have partest running, which actually runs Doty in parallel, compiling different stuff at the same time, and as of now it works. We had some pretty funny issues by trying to see why it didn't originally, and we had some bugs inherited from Scala C where the reader of Java class files had a global mutable state which was maintained between calls. So we were making a call for a utility library which was just storing the variables which should be local in a global scope, and well, it's not going to work in the parallel scheme. But yeah, that was based on our model, that was the only thing that ever exploded in the parallel case. Yeah. Yes, please, Adrian?
Yeah, so this is all great stuff. Great job. What's your personal view on how this is going to evolve?
Okay, the question was that it's great stuff, and what's my personal view on how it's going to evolve?
I'm asking because I think there are a lot of great things that I would want to see as soon as possible in mainline Scala, and there are other things that are probably going to take more time.
Yeah, so
I'm curious how you would approach it.
Well, so the little of the project is Martin, but I can share my opinion on it.
Yeah.
My opinion on it is that I would actually try and see which features make sense, but considering every feature, I will try to actually see how much code does it break. So for example, originally in Doty we had mixin working slightly differently than Scala C. It was fixing some of the annoyances that I had in initialization order and traits. And you actually can see intermediate values on our initialized values. I was trying to fix it. But after we did it, we understood that we actually changed some of the things that happened to work in Scala C and people happened to rely on. And we changed in the way that we're not sure if there could be a migration strategy in general. So as of now, every time we try to think a feature, we're trying to think on how much does it break, and whether we're able to provide you a rewriting tool which will just fix the code for you. So one of the features that we have that's incompatible with Scala is that in Doty, every time you have an implicit def or implicit val, you're required to write a full type for it. Doty is not going to infer type of implicits for you, because it's proven to be, well, to give unexpected results.
You should deprecate that in Scala.
Yeah. So the rewriting tool that we have now, just if it sees Scala C implicit, it asks Scala C to infer a type for it and just makes it explicit in the source. So it just works. Yeah. But basically, in Doty, indeed, given the pace at which we were moving now, we'll be able to introduce new features really fast. And honestly, I want Doty to be used by people. I don't want to be experimentation plant where nuclear rockets are being exploded. And based on this, well, I want to first play around with feature just in my branch and not merge it in master. So actually, if you'll have a look in the organization of Doty repo, so we have this lamppfl.doty, lamppfl standing for the laboratory, but you actually see that lamppfl.repo, this doesn't have that many branches, and the main reason that we actually have something called Doty staging here, where we're actually doing active development, and most of hairy stuff happens here. So this has enormous amount of branches, 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 branches. So yeah, so more bleeding edge is here, and occasionally it happens that my code in Martin is diverging in substantial directions, and then we're merging it back to the Doty upstream. Yeah.
Whoever's first wins. Whoever is first wins.
Well, we have more or less proper code review and proper integration tests, which actually, thank you, Adrian, are based on the type-safe infrastructure. So Doty, let me show you something about Doty test organization. So most of the Doty tests are defined here. For this case, I was planning to show how to test this particular phase. So in order to make it run faster, I had them commented out. But the way you do it is you say that's a test which consists of compiling the file in this directory with this name twice. The fun part is that sometimes compiling the file twice is not that easy as you think it is. It can create problems in compiler. And this task can actually be run by GUnit, by partast, and it can be automatically converted to benchmark. And we do all this in our continuous integration. So this is a run test. So you can also do the same with directory. Just compile all the files in this directory, and they all should compile. We also have run tests here. It's just this expects a directory which has run tests in the format which is defined by partast. So you have a file which is to be compiled, to be run, and a check file nearby that should be validated as a standard output of this file. Yeah. So we have, and additionally we have several self-contained GUnit tests here. For example, this thing is to test desugaring. Or so we have some quite testing here. But the biggest test for now is, well, compiling Doty itself. And we're not there yet. Yeah. Yes, please, Simon?
Have you any idea how Java compatibility looks, and especially around write paths, given that the type system is quite different in some parts?
So, as far as I know, Doty type system is more expressive than Scala is. And I mean, I have not tried to play around that much with Java wildcards, but as far as I've seen, Martin has some Scalumization around it, which, as far as I read the comments, is more expressible. I'm not sure if it's complete. Maybe it is. So I'm not sure if I'm the good person to ask. Yes, please?
Could you perhaps provide some kind of estimate of when this might be kind of production ready?
So what's your notion of production ready?
I don't really know.
I mean, if you want production ready, you don't want new features. You want scalacy. If you want new features, well, then you're not my definition for production ready, I guess. I mean, so in Doty currently we're...
will never be production ready yet.
Huh?
You're saying that new features will never be production ready?
No, I mean, it would take time for them to be production ready. The thing is that in Doty we're able to introduce new features fast. And it means that in order to actually stabilize Doty, we need to make an explicit decision about doing so. Currently we're still bootstrapping. Now you can compile small and medium-sized applications with Doty and they run. For example, the test suite of Scala Blitz compiles. But Scala Blitz itself doesn't because it uses macros. Doty itself compiles for no good reason that I'm yet to find out. The previous one was creating private members overriding public members. Yeah.
Okay, I'm afraid we have to end it here. So thanks again for the great talk, Dmitry. If you have any further questions, you can continue in the break, I guess.